in Turbulence by Tennekes and Lumley, and Turbulent Flows by Stephen Pope. And as I said, that these two may not be the only books, there may be some papers and some other references, which as and when we use, I will come to it. The first two lectures were mainly from Tennekes and Lumley, and when I come to the cascade theory, then I will sort of have text from both the books, not just one. And that's what. Okay. So now, in the last class, we looked up at a problem where we said that we had a length scale was given to us, the length of the room, and we tried to estimate the turbulent time scales given the length scales, and we talked of the ratio of the turbulent time to the molecular time. And what we found was that the turbulent time the scale was much less than the molecular time scale, which means mixing is much faster in a turbulent flow than in a laminar flow. Now, let us look at a problem with an imposed time scale. We saw the earlier example was one with an imposed length scale, where we talked of length of a room, and then we tried to deduce the time scales from the given parameters. We talked of a heat buoyant acceleration. So, once we knew acceleration and we had a length scale, we were able to deduce a time scale. Now, here the problem we will look at is a problem with an imposed time scale. And the example of this will be boundary layer in the atmosphere subject to Earth's rotation. Now, when we study flows with weather, then this becomes a problem where we have some people from atmospheric studies also. So, we are looking at boundary layer in the atmosphere, and the motion which is taking place is essentially the motion due to the rotation of the earth. So, in some sense there is air flowing on the earth, and because the earth is rotating, so therefore the air starts to move, and then we are trying to find the scales with respect to this. And what in particular we will try to do is find the laminar scale vis-a-vis the turbulent scale, and look at the ratio of the two scales. Which scale, if there is more mixing, then on an overall length scale, which scale would you expect to be bigger, laminar or turbulent, if there is more mixing? In an overall scale in a turbulent flow, what do we mean by overall scale? The effect till which we feel the mixing. So, if there is more mixing, will this global scale be more or less? It will be felt at a greater distance. Okay. So, for example, let us say if there is a small motion here, if it is a laminar motion, which we say has lesser diffusivity. So, then we would expect that motion due to this scale be contained very close to the surface. Whereas, if there is more diffusivity, then we will go to a greater distance. So, let us try to see if we can get such estimates, and again you will find here there will be many heuristic, many qualitative arguments to do that. Yeah.
Can we use the heuristic of a pipe having layers of viscous force?
Yeah.
For the Earth's rotation, having air above it and then layers of viscous.
Yeah. So basically, Earth is rotating. So because of the Earth's rotation, there is some movement caused. So then we are trying to see how much is the motion, what sort of motions are we getting because of that. And we look at laminar. For turbulence, of course, we will have to come to data or real life data to get some estimates. And once again, as I said, these are things which will be, so it's basically Earth's rotation. And here, when we talk of Earth's rotation, the major effect which comes in, the acceleration which comes in, is because of the Coriolis effect, and this is equal to two omega cross V rel. What is omega? Omega is the rate of with which the earth is spinning. What is V relative? The relative velocity of air compared to the surface of the earth. Okay? So that is what gives you this acceleration. In fact, actually, this is in sometimes when you keep the Earth's frame as the frame of reference and rotate with it, then the Coriolis acceleration comes as a pseudo force. The Coriolis force, it is sometimes called, but actually it's an acceleration. Okay. So now let's try to see here. So the order of magnitude of omega, this is the physical quantity which we have, the Earth's rotation. So what is omega? Omega is equal to 2 pi divided by I am sure everybody knows how we get 24 and 3600. Okay. So this turns out to be equal to something like 7.292 into 10 to the power of minus 5 radians per second, and we can take it as an order of magnitude as 10 to the power of minus 4. So this frequency is of the order of 10 to the power of minus 4. The time period associated, so f is equal to omega, I am writing it as a typical frequency. So the time period, what will be the time period associated with this frequency? What is the relation between frequency and time period? 1 over f. So then, because we have already taken the 2 pi factor, so this time period will be something like 10 to the power, and essentially it is of the order of 1 day. 10 to the power of 4 seconds basically will become 1 day. Now, if the boundary layer is laminar, then the length scale in a laminar boundary layer goes like square root of nu t, or Lm square goes like nu t. Now, how do we get this estimate? Once again, it comes from order of magnitude analysis or dimensional analysis. If the time scale is t and nu is the viscosity, then with these two things, the length scale which you get is square root of nu t. And what this tells you is that this is the effect which will be felt. Lm is the width of the boundary layer typically, and that will means in time t, because of nu, the smearing effect will be square root of nu t up to that extent. And once again, if we now try to put in the values, so this will nu t will be equal to 0.15 into 10 to the power of 4. I am using nu as 0.15 centimeter squares per second. So therefore, this comes out to be this, and so the laminar length scale of the boundary layer is of the order of 40 centimeters. So this is something like, suppose if the earth was at standstill and it starts to rotate with this omega. So by the time you complete one rotation, the boundary layer would have gone by about just 40 centimeters. So if the flow was laminar, nothing else, just molecular diffusion, this is the effect of how you would get.
Sir,
Yeah,
so the frequency, should it be approximately 10 to the power minus 5?
you can take it 10 to the power of minus 5, this number will not change too much. You can see, but we have taken this 2 pi also, na? So that is why it became 10 to the power of minus 4.
So the omega is 7.29 something, if you divide by 6.28 something, it goes close to 10 to the minus 5.
The 6.2 pi Need 2 pi divided by 24 into 360. I think this number is correct. हाँ तो ओमेगा इज इक्वल टू हाँ तो एफ कर लोगे ठीक है it's something like that. So these are just again as we said we are trying to see the order of magnitudes. But what we find is in observation, and this means with turbulence present, this L is of the order of 1 kilometer. Okay. So actually L is much larger. You do experiments and then you find that the boundary layer goes up till about 1 kilometer. So now the time scale is fixed. So that means what is going to happen is that we have, instead of nu, which was the molecular diffusivity, there is probably some other type of diffusivity, or which empirically we call as the eddy diffusivity. Okay. Now eddy diffusivity we have so far not introduced, but we replace, so we replace nu by k sub t, which we call as the turbulent viscosity. And what we say is the turbulent length scale will go like kT times T. Now from dimensional estimates, kT has dimensions of same as the dimensions of nu, which is meter square per second. Okay. So we take this as basically equal to a product of u times L, meter square per second. So it will be meters per second times L. Now because this is turbulent, so u will have to represent some typical turbulent u, and L will have to represent some typical turbulent length scale. Now LT we are saying is KT times T, isn't it? LT square, sorry. This typical velocity u, now this time scale T, we can replace it, we can, so what we have is, so first let us write this KT as u times LT times T. This is KT. And the turbulent length scale will be u times T. Basically, we are taking that the time scale is given to us in this problem. The time scale is coming from the frequency, and we are trying to determine what is u. Now, to get u, we use empirical data, and u is typically something like 1 over 30 times the mean speed in these flows. So, if capital U, the mean speed is 10 meters per second, small u is of the order of 0.3 meters per second. And based on this, we get the turbulent length scale as again, as I said, some of these things look like crude approximations. This is data which has been given to you. But right now, at least when you don't, at least this is a master's course, let's not get worried too much about exams. If it is an exam, then some of these things will be given to you. But in real life, when you do research, some of these approximations you will have to make. And that is what we have to learn, particularly those who are doing, even maybe not so valid for master's students, but for PhD students, definitely. And how do you check your assumptions? Finally, the assumption checking will come only on the basis of the final results. You will have one typical experiment. If your whatever assumptions you make, if your results match that, then you say it's fine. What I assumed was okay. Otherwise, you'll have to make some other, then that assumption may have been wrong. And that is how real life research progresses. You're never on a one-way track that you're just solving and you get through the answers. Yeah. Capital U is basically the mean speed this air would be flowing. So that is what is taken as 10 meters per second. In some sense here, this mean speed would probably come from this square root of, if you try to get a velocity from nu and t, you can get a velocity from these two things. Nu is meter square from nu and t, that should be of this order. Maybe I can calculate it, I didn't do it, but. So the crux here is that what we have are turbulent eddies of speed u. They are exposed to a Coriolis time scale t, will have a length scale of u times t. And this eddy size which we get, this small l is the size of the eddy. This is of the order of the turbulent boundary layer thickness. Now, in this sort of crude example which we have done, there are many learnings we can get to. One of the learnings which we get to is that we have talked of KT, which was a turbulent viscosity. So that means we are effectively trying to say that we, instead of a molecular viscosity, how this comes we have not talked about. There is, because the length scale is much larger, if it is square root of nu t, obviously that doesn't give us the right length. So since the time scale is the same, then means there is some sort of another viscosity which is governing this flow, not the molecular viscosity, which we call as the turbulent viscosity or eddy viscosity. Again, this is just a hypothesis. This is just a way to attack the problem. Otherwise, we will not be able to get any estimates. So this turbulent viscosity is also called at many times eddy viscosity. So this is the first learning we do here. From this sort of a crude way of working, we show that this is one thing we do. And secondly, what we do is, and which is again something very important, that we, from dimensional analysis, and some physics. What do I mean by physics? We use the fact that u was something like 1/30 of the mean speed. So this came from the observations from physics So we were able to guess that KT was of the order of U times L. Now this, a velocity times length is something which is mathematical. If I look at the dimensions of K, it is meter square per second, so it has to be U times L. But now which U and which L is what we got from our estimates, and here what we, our estimates to get this, what we did was, we said that time is still the same time. So first we converted it in terms of time, and then we worked out, we kept the same time scale, we got the U from some empirical data or physics, and then we worked out the estimate of KT. And then we got that KT was something like 3 kilometers. So now when you develop models like this on dimensional basis, then what you will do is you will write KT is equal to U times L comes from dimensional analysis, but to make it a bit more of the proper order of magnitude, you put a constant A, and this A is a dimensionless constant, and here our experiments, if the experiments show that LT is of the order of 1 kilometer, then A will turn out to be something like 1/4. So whenever you make a model and you put some dimensional things along with it, you always will also put a coefficient, and the coefficient will be determined by experimental data. For example, how many of you have used the K epsilon model? Has anyone used the K epsilon model? No. So have you heard of the K epsilon model? Now in K epsilon model, I will do it later, but what is done is you write nu t, and nu t is written as, once again you have to, there are two parameters which come, K and epsilon. Obviously it's a K epsilon model. So dimensionally it turns out to be equal to, nu will be equal to K square divided by epsilon. But when you write the model equation always says nu t is equal to C mu times K square upon epsilon. And this C mu is the dimensionless constant which you put, and the only way to get C mu is experimental data. You will not be able to derive this constant, dimensionless constant, from dimensional analysis. It will only come from empirical data. So these sort of things will keep on happening as we progress in the course, as we learn how to do the modeling. Okay. So now the dimensionless constant has to be obtained from empirical data. Okay. So now one more thing, let's now try to look at the ratio of these two, the turbulent length scale which we got to the molecular length scale. It was ut times square root of nu t. So this becomes equal to square root of u square t square upon nu t, and this will be square root of u times ut upon nu, so square root of u times L upon nu. So this becomes equal to square root of Reynolds number, where Reynolds number is based on the length scale of turbulent boundary layer. So, and this again shows the point which we were saying, the turbulent length scale, which anyway we have shown in terms of numbers, one is 1 kilometer, other is 40 centimeters, goes like square root of Reynolds number. Now in the time scale problem which we did in the last class, or in the length in flows, with imposed length scale, Reynolds number was of the order of the molecular time scale divided by the turbulent time scale. Whereas in flows with imposed time scale, Reynolds number goes like LT upon LM whole square. And the basic crux of both these things is that turbulence therefore causes much more diffusion than a laminar scale. Okay. So, this leads to the conclusion, the crux of the matter is turbulence is a much better diffusion agent. And this is, but we have to remember that this is in problems of only a single length scale or one time scale. Such analysis we can do, or what we have done. We had one length scale or one time scale, and we found out the other scale in terms of this scale. If it was a time scale, then we found length scale in terms of this. If it was the length scale, we found time scale in terms of this, and then we found the ratio of the two scales. If there are many length scales, many scales could come because of many things. There could be a particle, there could be some other motion which is taking place which causes a velocity scale. There could be small particles which are settling down. So, there the particle size could also come in and the container size could also come in. So, there could be two length scales. So, these are just, we are just starting off. So, we are looking at just some of the estimates which we can make from these scales. And this is just to introduce you to some of these things. So, next let us also look at another consequence or another such estimate. We will do probably one more before we come to the cascade theory, and this is, if we look at the, so if we look at this problem of the boundary layer. Now, this is the Navier-Stokes equation. The gravity term has been clubbed with the pressure term. We are looking at steady state equation. So, this is the general Navier-Stokes equation. And if we look at the laminar boundary layer theory, and again we do some estimates there. So, what we have is something like, if it is a flat plate of length L, there is a boundary layer going. This boundary layer at the end of the plate has a width delta. Now, all these type of flows where there is one main component of velocity which is a function of the second variable, these are termed as shear flows. That means, there is only one mean velocity in the x direction and it is a function of y. So, velocity is in the x direction, it depends on y. So, these type of flows are termed as, they may depend on x also, we will look at that, but these are termed as shear flows by and large. And one of the shear flows is this flow in a pipe, flow in a channel, flow in a plate. Jet flow is also a shear flow, and then there is another flow called a mixing layer, where you have a plate, on the top of it the flow has some other velocity, on the bottom it has some other velocity, and the plate just ends, and in the region where they mix, that is called the mixing layer. Again, that geometry I will discuss in detail when we come to that. So we have, let's look at the laminar boundary layer theory. And again, here what we do is we do order of magnitude analysis. So uj, and this you must have done, dui by dxj. So here we are talking of flow with a velocity capital U going past a flat plate. So this, again, except one or two of you, everyone would have seen this. And this uj dui by dxj, we do an order of magnitude and we write it as u square upon L. Okay? Because here what we have is this left hand side, this is the convective term. And in the convective term, the length scale is of the order of capital L. The flow is going with a velocity capital U on a plate of length capital L. Okay. Whereas when we do the order of magnitude analysis for the viscous term, this is nu d2u by dxj. Here the length scale, when we do this length scale, we talk of as delta or maybe small l. So let's first talk of purely laminar flow, and we take the length scale as, if I take the length scale is capital L. So then if you look at this, this term becomes of the order of nu u upon L square. And then when we take the ratio of viscous to convective term, this will be equal to ratio of, no sorry, the other way round. So we take the ratio of inertia term to viscous term. This will be equal to, so convective term is of order u square upon L, viscous term is nu u upon L square, and this ratio turns out to be equal to ul upon nu, and this is equal to, this is how, so when I am writing this, I am not even talking of the boundary layer, I am looking at a general flow, then that is how you get this, that ratio of inertia forces to viscous forces gives you Reynolds number.
Sir, didn't we say that the length scale for the viscous term is delta?
No, so right now I am taking it as L. Right now I am just looking at trying to get how do we get this expression that Reynolds number is a ratio of inertia to viscous forces. Okay. Then I am coming to delta L. Yeah.
And we switched from capital U to small u.
No, there is no small u. I will write capital U. There is no small u here right now. This is no, right now this is the speed with which the flow is coming on the plate. Okay. नहीं अच्छा एक मिनट, आई बी केयरफुल. कैपिटल यू में मैं हर बार ये दो ऊपर ये लगा रहा हूँ, तो अभी इसमें अच्छा वो जो वेलोसिटी थी दैट इज द वेलोसिटी फील्ड, विल कम टू दैट, अभी इक्वेशंस पे आएंगे तब विल. सो दिस यू इज द वेलोसिटी फील्ड. So capital U there is the velocity, just the velocity field. Now which mean or fluctuation we have not even talked about. So therefore it is just the instantaneous velocity. Okay. So now when we have large Reynolds number, then we would expect low viscosity, and eventually we would expect inviscid flow as Reynolds number becomes larger and it tends to infinity. But boundary conditions do not let this happen. In fact, I am coming to the essentially the crux of the boundary layer, starting off with why the boundary layer problem comes. That boundary conditions ensure that velocity at the wall has to be 0, far away it is capital U, and even as the flow speed increases, so what we say is that the effect of viscosity should go down and down. If it goes down and down, what should happen is even at the plate, the velocity should become capital U. But because of the boundary condition, the velocity has to be 0 at the wall. So viscosity does not let the flow become totally inviscid. And that was Prandtl's idea of boundary layer, that effects of viscosity are contained in a thin layer near the wall, where viscous effects are important, vorticity is important. Outside that region, the flow can be treated as inviscid, but within that region, the flow has to be viscous. And that this region where viscosity is important is what is termed as the boundary layer. Okay? So this was the idea of the boundary layer. So what we have is, so close to the wall, we have a thin layer of fluid where viscosity is important. So even Reynolds number may become higher and higher and higher. You cannot do away with viscosity. There will be a small region where viscosity is important. So what we say is, close to the wall, let the length scale of the thin region be small l. And then what you have is, now when you, this is the convective term, this will be of the order of nu u upon L square. So now we make this change, this is the convective term or the inertial term, and this is the viscous term, and on the basis of this what we can get is L upon L goes like nu upon UL to the power of half and if I make a cartoon like this now, that picture becomes valid, that this is of the order of small l or delta, this is capital L. So here this picture which I made here, this sort of I made it earlier than when I should have made this. So I have this capital L. So we have convection here, and in this direction is where we have the diffusion. Yeah.
How did you get to this relation that convective term is of the order of viscous term?
Okay. Now, what happens is that there are this convective term is of the order of viscous terms. This will come from the fact that in the flow we have these two terms which stay. There is a pressure term also, but then in a lot of for this flow, this argument of convection and viscous term being of the same order is the crux of boundary layer, that the time or the convection which takes place and the diffusion which take place, they will be of this. Now I am repeating the same thing. Let me try to see if I have to give you a reason why they have to be of the same order. It is okay. This is because we are talking, this will be of the same order in the boundary layer. Because in the boundary layer, viscosity effects cannot be neglected. Outside the boundary layer, this may not be true. But within this closed region, the viscous effects are important. And flow is being convected. So therefore, in some sense, to get an estimate of this L, we equate these two terms.
So, but at the boundary layer, the viscous term has to be dominant, right?
It is of the same order as the convective. See, convective term has to be there. Flow is convecting. So outside the boundary layer, the viscous term is of a much lesser order. But within the boundary layer, they have to be of the same order. What you are trying to say is, why is the convective term not 0? Or of that order?
I mean, that layer is
Ha. But in that layer, still the flow has to take place. Convection still has to take place. We cannot wish that away. Possibly that could happen in a case where we have a buoyant type of flow, where there is no capital U. See, here capital U is imposed. But a good question, I think. Yeah. No, we are in this. See, we are not. I'm not doing the boundary layer theory, but for this particular flow, flat plate, you can show that the pressure gradient is 0. See, actually, what happens is in these flows, the pressure gradient term comes, but pressure gradient is imposed by the inviscid flow. In the boundary layer, when we do an order of magnitude analysis, see, right now I have done only for these two terms. If I do an order of magnitude analysis of the x equation versus the y term, there are two components of velocity, x component and y component. Then what we find is y component is much smaller. And that order of magnitude tells us, when we do that partial p by partial y will be very small. That is what the boundary layer theory tells you. So this is all for a laminar boundary layer. And this finally comes, in the boundary layer theory, when we do it as delta instead of small l. Here you could say it's L laminar or L molecular by capital L is equal to Reynolds number to the power of -12. So this is the laminar flow. I'll just थोड़ा सा और चले जाए आगे, if you don't mind. So now what we find here is, for the laminar case, the diffusive length scale is L or delta, and the convective length scale is obviously capital L, and delta over L is small, and when delta over L tends to 0, this is when we get the boundary layer equations for a laminar flow. And these equations are much simpler than the Navier-Stokes equation. And this, again, that theory we are not going to do. I think there may be another class. What I'll do is I'll end here. In the next class, I'll continue from here. We'll talk of the turbulent boundary layer. This is just the laminar boundary layer. And this theory you would have seen. If you have not seen, you can refer to, I have my lectures on YouTube. So there are 4 or 5 lectures on boundary layers. So maybe you can have a look at that if you want to just study the laminar boundary layer. And there I have done the full theory, all the pressure, everything has been explained in detail, and the whole theory, how we work if we are got to use this analysis. But that is not of use in this course. We are just looking at the laminar. We'll talk of turbulent in the next class. Yeah, scroll up. वैसे नोट्स तो मैं डाउनलोड कर ही दूंगा. हाँ, ये क्वेश्चन है कुछ उल्टा लिखा है क्या? -12 होगा. हाँ, तो न्यू यू एल नहीं, ठीक है फिर तो ये यहाँ माइनस कर दिया था मैंने. ओके, ठीक है. वैसे गलती होगी तो वी कैन ऑलवेज, मेरी कई बार गलतियाँ हो जाती है ऐसे लिखने में, बट दैट्स फाइन. I'll upload this lecture today itself. First 2 lectures have already been uploaded on. Is anybody not on? I've added you, I think. On the Moodle site, I have added your name, Sanjeev. You have not been added? तो आज 1 मिनट ले लो, पूछ लो ये, क्योंकि पिछली बार बाकी किसी ने Moodle चेक किया है क्या? So you saw the lectures. First 2 lectures were there. So are you registered for the course? Yes. So then have you checked Moodle? तो you didn't see, you are not there. तो I'll add you. तो I'll add your name. ठीक, मैं ऐड कर दूंगा. हाँ, ये आई थिंक शुरू वालों के नाम है केवल अभी, तो मैं ऐड कर दूंगा, फिजिकली ऐड कर देंगे इनका नाम आज, ठीक है। ओके, एंड सॉरी आज क्या हुआ, लिफ्ट का बड़ा चक्कर हो गया।